talked a lot about ordinary global symmetries, anomalies, and we've learned some language to deal with discrete symmetries. And now we're going to really generalize and talk about something a little more fancy, which is higher form global symmetry. And the basic idea here is that, so we saw that symmetry, at least ordinary global symmetries, could all be reformulated in terms of topological operators with various properties. And that actually suggests a simple generalization, which is to look at topological operators of different dimension than we've looked at before. So what will be a Q-form global symmetry? This will be defined in terms in the following way. So first we'll have topological operators. We'll call them U, G. Again, they depend on a manifold. Now the manifold, instead of being d minus 1 dimensional, will be of higher codimension. So we'll put Q there. And Q is greater than or equal to 0. So as before, G in G is this is some group. We'll soon learn some restrictions. Actually, maybe we'll learn the restrictions now.
The usual is 0 form.
The usual is 0 form. That's right. So standard is 0 form.
So the form represents the parameter of the symmetry transformation.
Yeah, I'll explain the but yes, indeed. If we have 0 form symmetries, then this group G can be anything. If we have higher form symmetries with Q greater than 0, it means that G must be abelian. Why is that? Well, the multiplication law of these higher form symmetries is again encoded in some kind of fusion. So we want this fusion rule to hold. And now if Q is greater than 0, you can convince yourself that there's always enough room in space-time to move these operators around each other. So for instance, suppose I have two lines in 3 dimensions. This is G1 and this is G2. I would like to fuse them to consider G1, G2. But since everything is topological, I can just move this one around and then get G2, G1. So higher form symmetries are necessarily abelian. By contrast, for 0 form symmetries, these things get in the way. They're codimension 1, so there's no way to move one around the other.
More than up down, I was thinking out in, right? I mean, you were thinking you were acting like on a line.
Yeah, you can also squeeze it down, put it through, pull it back out, and bring it down. That's also fine. And the point is that it's just unobstructed. Okay, so good. So these are, this is the definition. Ordinary global symmetries are 0 form. And okay, so why call it Q form since the dimension seems to have this funny offset by 1? You could think of it in terms of parameters, but I also think it's good to remember that the objects that are charged under a Q-form symmetry have dimension Q. So what's the picture? So the picture is that we could have some extended object L in our theory, and we'd link it. If we can link it with some UG of the appropriate dimension, then this gives us some charge of L times L again.
Okay.
Yeah.
Crazy question. This equation here can be thought of as U being some sort of an operator valued first group homology, right? Element of.
Why did you say first?
It is just function of G.
Oh,
This is the relation, right?
yeah.
Is there a fancier structure which is operator valued, lives in higher group homology?
Not known to me, but maybe.
Just one more thing. So because it's abelian, this cosine thing is trivial. I mean, there is no phase now in this multiplication stuff. Yesterday you had the possibility of a phase here.
Good. So yesterday, so I stressed that I didn't have a phase. The phase that occurred there, you should think of as acting on states. The definition of the operators always has the right fusion, right? So what we mean that this equation is true, for instance, when we probe it with charged things. So just like for the ordinary global symmetries, the ordinary operators told us what the definition of the multiplication of the group was,
So
Same
there
here.
is a notion of the abstract operator versus the representation of those operators
Exactly.
in a space.
That's correct.
And that will have a pair.
That will have an analog here. There could be ambiguities, and those will be anomalies that we'll be interested in. Okay, good. So, so this is sort of the general definition. And let me say a couple preliminaries, and then the rest of the time today, we're just going to talk about examples of this. Okay, so two more preliminaries that we should discuss are what is continuous.
Actually, I missed this business for operators and states. If an operator has a certain relationship, I don't understand. If there's a relation between operators, mustn't that relation act on states? What does it mean that the operator has a relationship with it? If that relationship is not true with matrix elements.
Good. So when we define the ordinary global symmetry, the group that it is, we mean that we define it by saying that the local operators of the theory are in a faithful representation of that group. So we look at what's happening in the local operators, and then indeed correlation functions with local operators will be, the group laws will be respected. But that doesn't mean that acting in general on the Hilbert space that the group law will be respected. And in fact, in quantum mechanics, you can say that an 't Hooft anomaly is exactly a difference between the group law that you see on operators and the group law that you see on states.
But are you saying that the group law is obeyed only when you put vacuum on the right hand side? Because otherwise, if you put arbitrary states.
If you put arbitrary states, you won't. Yeah, exactly. Yeah.
Okay.
That's right. Yeah.
Okay.
Yeah. Okay. Good. So what's a continuous Q-form symmetry?
And in conformal field theory, you can get every state by acting with local operators.
This axiom is basically false, except for in like the Ising model or something. I mean, in gauge theory, it's usually false. I mean, I don't even think it's true in like free Maxwell theory. We could have like we have extended operators. We can act with those on the vacuum. We can't make those states by acting with any local operator in the vacuum.
Wait, if you had a theory on S, where in D dimensions you got a theory on SD, that's a state operator map.
But let's discuss. Let's not discuss states on a particular manifold. Let's look locally. So, in other words, let's just look in flat space. Then I think that if you have extended operators, in general, you can't make the states that they create by acting with local operators.
Yeah, the Hilbert space on R D minus 1 is different from the Hilbert space on S.
Right, so in other words, instead of considering S a sphere, just put anything with some interesting topology, and then you'll violate that axiom.
That's
So, yeah.
Isn't there something called the Ried-Scheider or something?
Ried-Scheider theorem.
Ried-Scheider theorem.
That does not, that's not directly related to this. I mean, it has some bearing, but
That essentially says that on a flat space you can create any state that you want by something, the operator will.
if you assume that the entire Hilbert space is created by local operators. That's part of the assumptions of the Ried-Scheider theorem.
So that's part of the proof, I mean, that's part of the statement.
No, the Ried-Scheider theorem says first all the states can be made by acting with local operators anywhere, and then you later prove that you can support it in a small region. That's the conclusion of the Ried-Scheider theorem. Okay, so good. Okay, so good. So just a couple more preliminaries.
I just summarize the last thing just to make sure I understand.
Yeah.
You're saying that there's a certain algebra obeyed in matrix elements with vacuum,
Mm-hmm.
but more complicated algebra is obeyed in more general matrix elements.
That's right.
So the Hilbert space splits into various irreps, and in some irreps you can have a phase, and in some others you may not. In particular, the irrep which contains the vacuum. Is that the idea that there's a the entire Hilbert space is a big thing, and in some of the irreducible representations it might have a trivial, it might have no phase at all, and in some others it would.
All of the states are projective representations, so that's what it says.
Sorry.
No, but then the one that contains the ground state, I mean the vacuum,
Sorry. Let me.
the phase is not there.
No, but there's ground state. See, in the quantum mechanics example, for instance, the whole point was that there's ground state degeneracy. Right? Whenever you have a projective representation, you have this anomaly, there's ground state degeneracy.
Yes, that's correct. So then
So then what I said was not right, you're saying. Maybe it's like the BC system where you've got a bunch of ground states, and if you act on the down state, then some things can happen.
I think it must. The point is on operator symmetries act as U, O, U dagger. So whatever phases are there will cancel in the multiplication rule of rules. Whereas when acting on states, they don't cancel. So they only act as one side.
But there's a question of the algebra. I mean, is this true or not? And I mean, I don't understand the statement that it's true of operators, but is not true when acting on states. What does that mean?
Well, I thought it's true when acting on operators. So like when you do U, O, U dagger and then you put U, G, G prime and while transforming operators, this is true. Like G into G prime goes to G prime.
Oh, I see what you're saying. Maybe that's right.
I mean, that's what I thought you were saying. If I'm wrong, you might be wrong.
Well, that's a way of defining it, and that's a way of, I mean, when we say U acts on operators, that's the way we mean that U acts on operators. And but the group law that we define for here, it comes from investigating that multiplication that we get.
So the point is, even if the operators U have a phase in the multiplication rule, with all the action on operators will not have phase.
Yeah. That-
Because the phase cancels.
I mean, I think this is sort of technically how it comes about, but I think that I want to give a better answer to Shiraz's question. So, I mean, I think when there are phase ambiguities, like there were in the projective representation case, it means that yeah, I mean, in the projective representation case, it literally means that there's multiple ground states. So the local operators can facilitate transitions between the states. But they can't, it's like, let's think of the basic example of SO3 and the doublet representation. So then the local operators you could think of as just being anything in integer spin representations of SO3. And the states all have half integer spin. And you can transition between them. You can transition between any of them using integer spin things.
It actually sounds very similar to what you're saying.
Just like
Yeah.
out of C, because
Yeah.
spin 1 is like the adjoint representation of
Yeah.
spin half
Yeah.
thing.
Exactly. So in SUN, suppose you had a group law made up to a center element.
Yeah.
Then you wouldn't see it in action on the adjoint.
Yeah.
But you would see it in action.
Yeah, maybe that's a good way of saying
Yeah.
it. Okay. Okay. Good. So, continuous Q-form global symmetry is what? So this should be clear. This is just a Q+1 form conserved current. Some things like that occur in simple examples, but most of the really meaty examples are when the symmetry is not continuous. Because typically, for instance, if you have a continuous higher form symmetry, the theory has to be free in some sense. So for instance, continuous one form symmetry might come about from a conserved two form. Well, would come about from a conserved two form, and you might get such a thing by a free Maxwell field, which is an example that we'll discuss. Okay. And then the second simple generalization is that if you look at networks, we'll discuss that case in detail in the next example. Okay, networks of Q-form defects. What are they? These are the same thing as flat Q+1 form background fields. So just as we saw that for an ordinary global symmetry, describing these symmetry defects was the same thing as coupling to a background gauge field. More generally, when we have these higher codimension symmetry defects, considering them is the same thing as coupling our theory to an appropriate flat background field. So should I elaborate on this, or people feel, well, okay, maybe I'll elaborate on one small point, which is how to, so if you have a flat Q+1 form gauge field, what's the interesting information in it? The interesting information is the holonomy. So such a gauge field has holonomy on Q+1 form, on Q+1 surfaces, Q+1 manifolds. Yes, we'll discuss a bit about that later, but let's ignore that for a minute. We'll discuss what the boundaries, the open surfaces mean. Okay, so Shiraz were describing the fact that networks of these Q-form symmetry defects are the same thing as flat Q+1 form background fields. So the special case of Q = 0 we discussed before. And I'm going to tell you geometrically how to interpret this. So if you have a flat Q+1 form background field, what's the invariant information in it? Well, it's just some holonomy, which is valued in this group G, whatever it is, on Q+1 manifolds inside your space-time.
Right. Sorry, just to get orientation for this. So in the zero form case, a defect was, the simplest defect was just a wall.
Yes.
Right, codimension one.
Yes, I'm about to draw this picture that you're suggesting, actually. So we have this wall. Here's G. And when we went through, the meaning of this was that there was holonomy G along a cycle that pierced this wall. That was the meaning when we had an ordinary global symmetry. And the meaning is the same, just the dimensions of these objects are different when we have a higher form symmetry. So when we have a higher form symmetry, we have a Q plus, this will be a Q plus 1 manifold here. Where we're measuring some kind of Wilson surface. And this is the symmetry defect. And the meaning of this symmetry defect is that it induces a holonomy G as we cross it.
Now, in the case of the usual zero form symmetry, we could think of the wall as not implementing the symmetry transformation on the left and implementing the symmetry transformation on the right.
Yeah.
Is there an analogous statement here?
Yes. So you should chop up your manifold into yeah. So the
Firstly, what is the analogous statement about the symmetry transformation? Is there symmetry transformation associated? So far, you talked only about charges.
yeah. So we could. I mean, if we look at a fixed time, then we could put one of these higher form symmetry generators on any manifold in space, and that gives us an operator on the Hilbert space.
Good.
So if we have interesting cycles in our space manifold, we'll get a bunch of different operators on the Hilbert space.
Good.
We have.
The operator is not integrated over a d minus 1 dimensional surface.
It's not. It's integrated over a submanifold of space.
So it doesn't act on all of a state. It acts on some part of the state.
If you like, yeah. Now, good. Now, what was the second thing you asked?
I'm sorry. It's all part of the same question. I'm sorry to
Yeah.
be so
No.
scattered. It was that I just want to understand in terms of transformation of fields.
Okay. Good. So,
Does it generate some transformation of fields?
yes. Maybe let me do the first example, and then we'll where we see how it acts on fields, and then we can.
Okay, and just to keep the second question in mind, it was like this. It sounded to me like your wall, which was codimension 1, split space-time into left and right.
Mm-hmm.
So you could implement a symmetry transformation on one side and not on the other.
Mm-hmm.
Now suppose you've got like Q is 1,
Mm-hmm.
you've got codimension 2, so it's not splitting space-time into anything.
Yes.
So it can't be doing that kind of thing, right? It's doing something else. So I just wanted to understand what, just intuitively.
Okay. Let me see if I can answer it quickly. So I think the main thing is to so you could think of it this way. So if you have a background gauge field, ordinary background gauge field, you divide space-time into patches, open sets. And then the symmetry defects are things that live at the intersections of the patches and tell you like sort of how to connect left and right.
Yeah, like a Wilson line, as you say.
No, it's codimension 1. It's the thing that lives at the.
I understand, but
yeah.
that's what a Wilson line, because you can trivialize it except at one point.
Exactly. Right. So if we have a one-form symmetry, the interesting thing is now happening at the triple intersection of the patches. Okay. Now, in particular examples on fields, we'll be able to see something a little more concrete. So, okay. So, so this is kind of general definition.
Sorry.
Yeah.
You might explain the answer to that question again when you do an example. Really?
I will try. Yes.
Thanks.
Okay. Okay. Let's see. Okay, and finally, yeah. So 't Hooft anomalies will again be some kind of ambiguities that we find, some phase ambiguities when we try to do topological manipulations of these defects. And we'll see again some concrete examples of that. Okay, so what's the most basic example? four-dimensional U1 gauge theory. Free, no matter. Okay, so what's the one-form symmetry? So there's no zero-form symmetry of this theory, but there is one-form symmetry. And it's U1 times U1. You can think of one of them as being electric, and one of them as being magnetic. So what are the currents? The currents are F and star F. Okay, so what does that mean the associated surface operators are? We're in 4 dimensions and we have a one-form symmetry, so we're trying to define surface operators. That's the correct codimension. So the electric one is labeled by some phase alpha, because it's U1. I'll put E to remind us that it's electric. And this is e to the I alpha. We usually put a 2 pi here. Integral, and we take star of the current. So it's integral over some 2 manifold of star F. The magnetic one looks similar. But here we'll now have F. Okay.
The sigma 2 is like the world sheet of a vortex string, right?
Yeah, you could think of that. And that's even, yeah, it's even a real dynamical string in the kind of Higgs phase of the gauge theory.
What does it mean that the theory has this symmetry? It's some conserved operator that you promote to a current, you just call a current.
Well, I mean, the divergence of this and the divergence of this are 0.
Yeah, so that is the requirement, right?
So that's what it.
Theory, if I find like a 5 form of, some higher form operator.
Yeah. So this is, I mean,
does not stay.
right. This, yeah. That's this. Okay. So now we're going to investigate what does it do on fields, what's charged, et cetera, et cetera, et cetera. Trivial. Why are they trivial?
Starification is Gaussian to write it as a product of.
You can have a line operator.
Okay. You have charge operator.
Who is that? So you don't have to have charge field if you have an operator.
Yeah.
Same reasons, those things.
Okay. Good. So let's first say how it acts on fields, since that was just a question. So so this one has a simple action, the electric one. On A, on the dynamical gauge field. Namely, it shifts by a flat connection. So before I derive that, let me just point out that the action, of course, is F which star F. And so if you shift A by a flat connection, that's some kind of transformation of the fields. That's the symmetry of the problem. And you might have wanted to know what is the current, the Noether current associated to that symmetry. Okay, so how will we, I will prove this to you. So we're looking at this guy. So let's pick some coordinates. Let's go make it very explicit. So let's first step be in temporal gauge. So AT is 0. Next step, we'll take this manifold sigma 2 to be the xy plane. At t equals z equals 0. So this implies that the integral of sigma 2 of star f is the integral over dx and dy of partial t of a z. Okay, so now we can take this operator and we can conjugate. So we can consider U alpha E, where my sigma is this sigma, AI U alpha E inverse. So it's AI if I is X or Y. But since this is canonically conjugate to AZ, we get an interesting shift of AZ. Namely, we get AZ plus alpha delta of Z. So this is the shift by the flat connection that we were talking about. So this tells you how it acts on fields. Acts to shift the connection in this way. And the magnetic guy doesn't have a simple action on the fundamental field, but has a simple action if you went to some dual variables.
This is something that can be calculated.
You just cross out, right?
Yeah. I'm just saying that since this is the canonical momentum conjugate to AZ, conjugation just does a shift.
Yeah. And the magnetic guy doesn't have simple action because it doesn't have an entity. Right? It's no
Yeah,
momentum.
that's right.
So it just commutes with the A's, but it will not commute with E's.
So this is equal time commutation relation. As a result, there is no delta function of t, of course. It's just
Yeah.
delta of z. So there's some surface.
So I put everything at t equals 0. Yeah. Okay. Good. So it might also be simple to think in terms of disorder operator, which is maybe a good answer to your question. So you could ask, if I insert this operator UE, how does it modify the path integral? Well, we want to do this, but actually, first let me say what the charged operators are, and then we'll come back to that disorder definition. So the charged objects I erased it, but for UE, it's Wilson lines. That's because star F integral measures electric charge. And for UM, it's magnetic charge, magnetic lines that are charged, up lines. That's because F measures the magnetic charge.
So you say that the local action of this is trivial because it's not changing field strengths.
That's right. Yeah. Now, I want to give you this disorder definition because I think it might be a more satisfying answer to your question. So you could ask, suppose I want to do a path integral with this operator inserted somewhere. What will I do? So what I will do, it's codimension 2, so I'll look in a plane. In a plane, it looks like a point. So here will be, say, UE alpha. And I define the theory by a path integral over A's such that there's holonomy e to the I alpha around the cycle here. Around the defect. So that's how you define it in a sort of disorder-like prescription. You modify the definition of the path integral in that you only now integrate over fields where there's a fixed polynomial around this defect. So this is an example of something called the Gukov-Witten operator.
The junction of these other guys, four-dimensional one guys, can be decorated with these operators.
Yes, I wrote a paper about that last night.
Then you would have G1, G2, G3 equals not.
Then it will be, yeah, I'm happy to talk to you at length about that. Okay, so good. So this is the disorder definition. Similarly, there's of course a disorder definition for the magnetic guy.
Wait, and we should be able to see that this is the same as the definition of that insertion?
It is, yes, because this. So let's measure the Wilson line around here. So when we put the Wilson line around here, we get, since the Wilson line is the charged object for this thing can be deleted. The defect can be deleted, leaving the Wilson line plus the charge. The charge is e to the I alpha, if it's the basic Wilson line. So it's as if I shifted the gauge field going around here by e to the I alpha d theta. Okay, so good. So since we have these two one-form symmetries, we can couple to background fields, and since everything is continuous, everything is very explicit. So let's do that. So background two forms. So we'll include in the Lagrangian the following couplings. Bm wedge F plus Be wedge star F. Now these are background gauge fields, so they have background gauge transformations. Bm goes to Bm plus d of some one form. Let's call it 1. I'll put a superscript 1 to remind you that it's a 1 form. This is a 2 form. And Be shifts to Be plus d of some different 1 form. Okay. So if Be is 0, and we just look at this gauge transformation, it looks totally fine. F is closed, because we can integrate by parts. Similarly, if Bm is 0 and we look at this gauge transformation, it also looks totally fine because d star F is 0 by the equation of motion. But if both of them are on, this action is actually not invariant under gauge transformations. So this is going to be our first example of an 't Hooft anomaly. Okay, how will we see it? So let's, for instance, set Be to 0. Okay, when we do that, the equation, and we can recompute the equation of motion in the presence of background Bm. D of Bm will act like an electric current, because this is like A mu wedge star dBm. So the equation of motion is now the following: d star F equals d Bm. That's the modification of the Maxwell equation. So in particular, star F is not conserved. Now suppose we do a gauge transformation. So Be was 0. Let's just modify that by a gauge transformation. So we change Be from 0 to d of lambda tilde 1 then the action changes. It's not invariant. So here I get, if I plug in, I get d lambda tilde 1 wedge star df. I can integrate that by parts to get the integral of lambda tilde 1 wedge dbm. So this is an anomalous transformation of the action. The action is not invariant under gauge transformations of both of these. And you can think of what's the anomaly inflow action. We talked about the fact that anomalies are characterized by local terms in one higher dimension. And inflow action.
Wait, what happened here? You had d lambda tilde was wedge db. And then when you take the d, where did the d go?
Here, I put d lambda tilde, and I have it wedged with star f.
Oh,
And then I integrate by parts and use this.
Okay.
Okay, so the inflow action is the integral of BE wedge dBm.
This guy, the extra term doesn't change the equation of motion?
That's why I started by setting BE to 0.
Oh, you're saying that the equation of motion should be same to as the gauge transformation.
That's why I started in this case. More generally, you can do this calculation with both of them, and the exact form of the anomaly that you get will depend on what quadratic terms, what local terms you add in BE and BM. Remember, we discussed that you can have local terms that are not gauge invariant to modify the presentation. So in this way of doing it with no local term here, I've given you the form that is this. But you could, for instance, by adding local terms, get the form where you move the d over here, or something that looks a little more symmetric. Okay, but anyway, this is our first example of an anomaly in a higher form symmetry.
Such a term you need these, you cannot write such a term for the same, right?
For continuous two forms, you cannot write you cannot write such a term. That's right. So that's why at best there could be a mixed anomaly.
This is one of this reduced type of, this is this reduced anomaly.
Reduced.
Because in t plus 2 dimensions it will be product up to 2.
Yeah. So I've written it in 5 dimensions. Since it's continuous, you could go to 6 dimensions, and you could write it as dBE wedge dBm.
And then it's reduced because it's.
And in that form, it's insensitive to any counter terms that you write here. But anyway, I prefer always to think about inflow actions in one higher dimension because that's the thing that universally exists. Okay. Okay, so we can ask what happens to this story if we add electric charge matter of charge n. So in this case, the U1 electric symmetry will be broken to Zn. Why is that? Well, you could think of since we have dynamical matter of charge n, you could think of them, a massive charge matter of charge n being something like a Wilson line. And then that can screen, since it's a Wilson line of charge n, it was charged under the one-form symmetry. So we'll break down to the subgroup on which it's uncharged. Similarly, if we add magnetic matter of charge m, this U1 magnetic will break to Zn. Okay. Finally, there was a question about
So these would be strings now?
strings.
No.
No.
Does it matter?
No. Just ordinary fields in the Lagrangian of electric charge n.
You can think of the ordinary fields as having well.
Yeah, that's right.
How does it work in the four-dimensional one case then? Because that's because those also have well lines.
Mm-hmm.
Maybe I'm thinking about it. Yeah, but
The dynamical well lines that break that symmetry.
Yeah.
Like dynamical simulators.
Yeah.
So why are you doing this dead end?
Maybe the only case we have some.
Well, why did it break to Zn as opposed to as a?
They're supposed to like nothing.
Oh, because the Wilson line. If you think of this as a dynamical Wilson line, it carries charge n. So it can only screen things of charge n. Okay. So finally, there was a question also about whether these symmetry defects can end. Let me say that in this context. So for instance, if we have a magnetic surface defect, which is semi-infinite, going off this way, you can ask, what can it end on? And it ends on an improperly quantized Wilson loop. That is something that's not a genuine line in the theory. So how to see that? So remember that u alpha m was e to the I alpha over 2 pi integral over sigma 2 of f. And this is e to the I alpha over 2 pi integral of a along the boundary by Stokes' theorem. So if alpha had been 2 pi times an integer, this would have been a Wilson line actually in the theory. But the end point here is not a proper line. It's a line that has to have a surface attached to it.
why didn't we talk about boundaries of the ordinary?
You can talk about them as well. You should talk about them as well. They're important. This construction where you have symmetry defects that end is important when you discuss gauging the symmetry. I didn't really discuss that yet, but maybe I'll just say a few words about it now. So if you gauge the symmetry, what does it mean? You sum over these defects, right? Because the defects are flat background gauge fields. So gauging the background gauge field, promoting it to be dynamical, means summing over the defect configurations. And when you do that, you make these things transparent because you're summing over them. So in that case, this would become a genuine line in the theory. Similarly, if we had an ordinary symmetry defect that ended on something, that new thing would be a genuine operator in the theory. So for instance, yeah, that's right. So for instance, in 2 dimensions, ordinary symmetry defects are lines. And they can end on some kind of ray operator. But if you gauge the symmetry, you make this transparent and you get a new local operator. That's the standard twisted sector. So that's how it's described in this language. This also is a useful way of figuring out what new sorts of operators do you get when you gauge. So for instance, in 2 dimensions, if we gauge a zero-form symmetry, we get a new local operator. But in 3 dimensions, if we gauge a zero-form symmetry, we'll just get new line operators. Because symmetries, ordinary symmetries are surfaces, and they end on lines.
And those operators are now higher form
No, not in general. We'll discuss. I'll discuss that a little bit. What happens to symmetry when you gauge? But in general, they're just new defect operators in your theory. Okay, so that's why one is often interested in what the ends of symmetry defects are. They tell you what the new things you would get if you gauged would be.
So if what we just outlined, a higher form version, exactly a higher form version of Dirac's, what is it, monopole line operator and so on. Dirac monopole has this line coming out of it, and because it's gauged only the endpoint is fixed, it's a new point operator. Is this exactly?
Yeah, you could think of that. This is the theory of what the higher form symmetry defects can end on tells you exactly what the kind of improper versus proper, the genuine versus ingenuine defects of one lower dimension are. We'll actually use that explicitly in a minute.
Thinking about it in the context of Dirac string, it's a bit difficult, right? Because string is so much codimension. That's very high uniform symmetry in codimension. Is there such a thing?
Direct string.
That would be a two form, right?
No, I think.
It is exactly the same case.
Well, I think if I had done this for the electric defect, I would find that it ends on improperly quantized 't Hooft lines.
This should be translated in time. So
Yeah,
actually-
yeah.
So the
Yeah.
monopole is
Itself,
sheet.
itself, it will be sheet.
Yeah,
So it's
exactly.
that.
Yeah, exactly. Okay, this is all I want to say about 4D U1 gauge theory. I'd now like to do a fancier example, which is 4D non-abelian gauge theory.
Sorry, this is a vague question. But this operator that you define, let's say the electric operator, if you evaluate it on a spatial slice, on a sphere that goes to infinity, it also measures something else, right? It measures the zero form charge under U1 global transformations. It measures the net electric charge of the system.
Okay.
So that same operator, that operator plays a role in undergraduate physics, right?
Mhm.
It's what you use to measure by Gauss law,
Mhm.
the net charge in your system.
Mhm.
And now you're giving that, of course, that is not, as you, in a theory with charge, it's not a conserved, it's not topological the way you say it. So you
Mhm.
bring it in and you get some different stuff.
Mhm.
But I was just wondering whether that interplay was useful for you.
Well,
The charge in the RDA.
No, the charge of the gauge, even in the gauge theory, the global part is a conserved charge.
I think
Number
that
of electrons.
yeah, I think that in general, it's quite tempting to speculate that in spaces with spacetimes with boundary, like Minkowski space, a language for describing, say, this Strominger asymptotic symmetry analysis is somehow present in this higher form symmetry business. No one has yet explicitly made that dictionary. I mean, what you're talking about is like the zero mode of that somehow. But I think that it's very tempting to believe that there is a dictionary there.
Okay.
But isn't that charge of electrons exactly the same as this higher form electric charge? Because the electrons can be thought of as having some order lines.
Right, but let's think of QED. So the electrons are dynamic. Okay, let's say with charge 1. Then this higher form electric charge is not there, right? Because it's not a topological operator. You bring it in, some of the electrons will be outside. But at infinity, it's still
It's still there.
there.
Yeah.
these transformations should be enough to measure the charge of the electron. I mean, that's how normally we think.
Sure. Yeah. Just the zero mode is enough.
Just a zero.
Yes, just the zero mode is enough. But I think even more generally, it's probably the case that the other asymptotic, the infinite asymptotic symmetry algebra that Strominger talks about could be reformulated in terms of this, in terms of these operators. No one has done that. It's, and that's kind of a speculation, but it seems like the right language. Okay, so we're going to do 4D non-abelian gauge theory. What do we want to call the gauge group? Let's call the gauge group H. And the one-form symmetry will be sensitive to the global form of H. So let's first discuss an easy case. So let's suppose that H is simply connected. So e.g. SUN. So what are the allowed, so since we're going to say that there's one form symmetry that's controlled by the global form of H, a closely connected question, since there's one form symmetry, will be what are the allowed lines? So let's also discuss that simultaneously. So first let's discuss the allowed lines. That might be easier. So if we're having a simply connected group, then the allowed lines are, so the electric ones are Wilson lines in any representation. And for this form of the group, the 't Hooft lines are fewest. So the 't Hooft lines are those that are mutually local with all representations. Maybe actually, as an aside, as a useful thing, I should flesh out what that is for SU2, since it might not be so familiar. So let's put it up in the corner. Let's consider SU2 versus SO3. So for SU2, we can have Wilson lines with electric charge 1/2. And then in this convention, the 't Hooft lines would be charge 2. This is their magnetic charge. For SO3, things would be sort of opposite. We'd have Wilson lines only in representations of SO3. So in these normalizations, the allowed electric charges would be integers. But then the magnetic charge can be 1/2. So that's a little reminder about the difference between them. So, so here we have Wilson lines in any representation R. But if we're just doing, I should say here I am only have a dynamical non-abelian gauge field, no other fields. So those dynamical fields only carry adjoint charges. And so most representations, or many representations, can't be screened. So you could look at R modulo the root lattice. And you can ask, so the root lattice are the charges carried by the adjoints, the dynamical fields, and you can ask if there are if this is a charge that can be measured by some symmetry, and that's what we're going to do. So I guess I can delete this. So the one-form symmetry in this case.
For SUN, that would be like anality of the vector.
That's exactly right. So the one-form symmetry will be Z of H, the center of the group. So for SUN, it's Zn. And the Wilson lines exactly carry these charges. You could again ask, how do I define the defect? And now we've learned that one way to define it is by a disorder operator. So these surface operators have the same disorder definition. So if I put it looks like a point in a plane, since it's a surface operator in 4 dimensions, and I demand that as I consider only field configurations where as I go around, the holonomy is some element Z in the center of the group. So that's the disorder definition of this surface operator. Okay. So as was discussed for SUN, the charge of a representation is the number of boxes in its Young tableau modulo n.
And now this is the only definition.
This is the only one. Well, it also shifts a similar thing is that it shifts the gauge field by a flat connection valued in Z. But there's no integral. That's right. It's kind of the hallmark of discrete symmetries that in general they're, well, this is even harder than typical discrete symmetries. Okay, so as before, we could ask we could ask about, for instance, surfaces that end. So these surfaces can end on the forbidden 't Hooft lines. So since we have the simply connected form of the group, where in this case we have not all of the conceivable 't Hooft lines. Here we have only the even charge, but there was also this guy of odd charge. And you could ask, what's its role, say, in SU2 gauge theory? And the answer is that you can here, say for SU2, you can put the Z2 center defect. And it can end on the charge 1 't Hooft line. So that's it parallels our discussion before, except for that it's much less explicit because we don't have the expression where we integrate f or star f. We just have this disorder definition.
Is there another one-form symmetry?
No, in the simply connected form of the group, this is the only one-form symmetry. Okay. So now what I'd like to do is I'd like to discuss gauging this one-form symmetry.
So can you remind me, in 't Hooft's old discussion, he had this kind of linking between 't Hooft and Wilson lines with this kind of Zn. And that was probably on a spatial slice.
Mm-hmm.
So is that just taking a spatial cut of what you're talking about?
But I think he was discussing. No, I don't think so, because I think that he was discussing the linking of the lines that genuinely exist in a fixed form of the group. So I think he would be discussing the linking of these, or the linking of these. Yeah, I should say Toft was the one to realize that this is some kind of charge.
So the charge through line in SU2 is still charged under this one form symmetry.
This,
Through lines in SU2.
no, sorry. The Toft line ends on this. The charge things are Wilson lines.
So the two lines are not charged at all.
The Toft lines do not carry any one-form charge in this theory. Right? The charge things under this one-form symmetry that I defined here is sometimes called the electric one-form symmetry. There's not a magnetic one-form symmetry, so that's slightly a confusing definition. But the things that are charged are Wilson lines, or more generally dions, but it measures their electric charge modulo the root lattice. Okay, so now suppose we gauge, let's gauge a subgroup gamma of the center of H. So we're now gauging a one-form symmetry. We know what that means abstractly. It means, well, there's some gamma valued 2 form that we're gauging, and more generally, we're summing over configurations of these defects. What will we get? So the claim is that this should produce H mod gamma gauge theory. So we're going to produce a different global form of the group by gauging the one-form symmetry.
Just to go back to
Yeah.
this. So, I mean, only this kind of a rule that half versus 2 and so on is that what kind of lines of force can end at what kind of charges? In other words, what kind of fields can be screened, but what kind of objects? That's what gives me these rules that half can only end, half kind of lines of force can only end in. It has to be exactly dual in the sense of the weight lattice.
That's correct, yeah.
How is this avoided here? I mean, is it like?
Well, here, I mean, this is not a genuine line, right? This thing is not a genuine line. So this is not local. The reason I excluded it here is because it's not local with respect to the Wilson line.
Still there.
It doesn't satisfy integral Dirac quantization.
Which means that this thing cannot end. This defect operator cannot end in the theory itself. It's not a gauge invariant operator.
No, it means that the charge 1 Toft line as a line cannot be defined. The closest that you can get to it is to say that it bounds a surface.
But as a surface with a boundary, it's well defined.
That's correct, yes. I mean, if you think about the mutual non-locality argument, if you said that it was a surface, it's allowed to depend on the topology of the sheet that it extends, then you wouldn't have any problem.
Yeah.
Right? That would be where the branch cut is, for instance. Okay, so right, we're going to gauge this this one-form symmetry, and the claim is that we'll get this new global form of the group. So if you ever wanted to know what is the relation between, say, SO3 and SU2 gauge theory, they differ physically in that this one is obtained from that one by gauging a Z2 one-form symmetry. And that actually is helpful to organize many of the properties of these gauge theories. So, for instance, H mod gamma has more gauge bundles than H. So again, if you don't like general H, come back over here. SU2 has fewer bundles than SO3. Every SU2 bundle is an SO3 bundle, but not the other way around. And so when we do SO3 gauge theory, we're instructed to sum over more bundles. How are we doing that? Well, we have some additional Z2 gauge field now that is dynamical, and we're summing over SU2 bundles and over these Z2 bundles, and they're interlocked. Okay. So I can.
Traditional magnetic monopoles are like sort of twisted sectors,
That's right.
and the removed guys are like projection.
That's exactly right. Yeah. Yeah. That's right. So as was just said, so this gauging gamma supplies the new lines from twisted sectors. So if we go over here, when we gauge Z2, this sheet becomes transparent since we're gauging it. Now this line is just a new genuine line in the theory. And that's the new missing line that we needed. Conversely, we have to throw away this Wilson line because it's charged under the thing that we're gauging. So that takes us exactly to the correct spectrum of lines that we wanted.
So what we showed is that the spectrum of lines is the same as the one in the SO3 theory.
Yeah.
But is there a more direct way of seeing that it's actually the SO3?
Yeah. If with more time, you can actually just write down. There's a kind of trick for writing down the SO3 action in terms of the SU2 action using this. I can show you that afterwards. Essentially, what you want me to prove is that there's a dynamical Z2 gauge field. Let's stick to the SO3 language just so everything's clear. There's a dynamical Z2 gauge field here. So you could think of that as describing some, that gauge field is some element, omega 2, in H2 of the space-time manifold with coefficients in Z2, some cohomology class. It's Z2 one-form gauge field. And what you would like me to prove is that this dynamical two-form gauge field is the Stiefel-Whitney class of SO3 bundles. So it's the thing that you additionally need to sum over when considering SO3 versus SU2. And that can be done. Okay. Okay, good. So we're kicked out of here in 7 minutes, right?
Yeah, I think so.
Okay, so I'll have one final thing to say then. Okay, so let's now discuss what happens to the one-form symmetry. Okay. Okay, so the first answer is that, well, you take the center, and we gauged this. So the new one-form symmetry is that. That's what you might expect. But this answer is actually wrong for an interesting reason, which is that discrete symmetry, as many of you who are familiar with, say, 2D field theories know, is very hard to kill by gauging.
Quantum symmetry. It's the thing, the quantum symmetry group of the obofold.
That's right. So I'm going to now tell you the general version of that. So discrete symmetry is hard to kill. What does it mean? So suppose I have, this will be an aside just in general. Suppose we have a partition function let's call it, okay, unfortunately this will also be called Z, but such is life. Okay, of d-dimensional theory with discrete Q-form symmetry. That means I can consider the partition function of this theory in the presence of B, which is a background Q plus 1 form field. Okay. What does it mean to gauge? To gauge means to sum over B. And I stress that since I assumed everything is discrete, this is really just a discrete sum. There's just a finite number of terms. Sum over. So this defines Z tilde, we need more space, Z tilde, the partition function of the gauge theory. But there's a simple way to modify this sum, which is that I can include e to the I integral of B A. And I can use this to define Z tilde of A. And A is a D minus Q minus 1 form. So my new theory has a D minus Q minus 2 form symmetry. And you
Sorry,
can,
I go back to my previous question. What does it mean to have the symmetry now, because there is no
so because I made this thing dynamical,
current?
there are now Wilson surfaces for this dynamical field. And those Wilson surfaces are symmetry defects in the new theory.
So even going back, when you started with this whole example, when you started discussing the non-linear theories and the fact that there is a electric, there is a Z symmetry, what was the meaning of having this symmetry? Because in the previous case you had an explicit current in future.
The meaning of it is that there are codimension 2 topological defect operators, which obey the abelian fusion algebra given by the center of the group. And the definition of those defect operators was as disorder operators in the path integral. And this is very formal argument, shows you that, and I should say here that if the symmetry group, the discrete group here was G, you'll get the same group here on the other side, G. So some familiar cases might be a zero form symmetry in D equals 2 dimensions. Then you start with a zero form symmetry and you get the zero form symmetry back out. But if you're above 2 dimensions, you see that if you, it kind of depends what you get out, what you put in. So anyway, in 4 dimensions, if we start with a 1 form symmetry, we get back out a 1 form symmetry if you plug into this. So over here, we'll get a new 1 form symmetry. This you could think of as a magnetic 1 form symmetry.
This is just, in the SU case, it's the statement that either the electric charge quantum was minimum or the magnetic charge quantum.
That's right, yeah.
So, yeah, go ahead.
Now, the magnetic 1 form symmetry actually has a somewhat more explicit representation in terms of asking how do you measure the charge. The point is that in say, SO3, we have this Stiefel-Whitney class, which is an invariant of an SO3 bundle. So it's a G of X with coefficients in Z2. And I can measure magnetic charge by integrating the integral of W2 along some surface. This is a mod 2 measure of electric charge. Okay, I guess I better stop here since we're at the end. This is all I wanted to say about non-abelian gauge theory. Anyway, but feel free to ask me more if you want.